Hello, community. You know that modern LLMs have a problem with long sequence length. Then they have been pre-trained on, this is for example 4K token length for the Llama 2 model. Now, in one of my last video about long LoRa, I showed you how we can build a Llama 2 model with 100K token length. But today we look at something new. We look at a streaming LLM, a work here by Meta and MIT, Massachusetts Institute of Technology. And if you ask streaming, you mean data streaming? Yeah, we look here at full power data streaming that goes to an LLM, and the LLM has to respond to the data influx. So let us here have a look at this research paper from end of September 2023, MIT, Meta, and Carnegie Mellon University. And as you see here, efficient streaming LLMs with a new term, and let's have a look at this paper. Now, they say that there's a problem because this caching the previous tokens, key and value states consume extensive memory in our LLMs. And as I told you, LLMs cannot generalize to longer text than their original training sequence length. Except you do, as I told you in my video, when we go to a Llama 2 100K model with the LoRa implementation. And they say, yeah, one solution is a window attention, where only the most recent values for the key value pairs are cached, but they think that they found a new methodology. So let's dive into research for streaming LLMs. One sentence that caught my eye was here, based on the above analysis, we introduced streaming LLM, a framework that enables large language models trained with a finite length window, let's say of 4K in the case of Llama 2, to generalize to infinite sequence length. I love infinite length, without any fine-tuning. And you might say, this sounds like a logical contradiction. How can you do this? Well, it's a publication by a very particular company. So how can we build a finite to infinite system? And you say, what is the simplest case I can think of? Here we have an LLM, and here we have a data stream. And the data stream comes in, runs through. So we have a finite LLM, and we have an infinite amount of data that could theoretically be streamed over thousands of years to an infinite length. Now, important is here in this implementation that we have a linear sequence of data, and you say, I get it, where we are going. So we have now this stream of data coming into our LLM, and at a particular sequence, at a particular detector sequence, we have that the LLM says, hey, I found something, I detected something. So whenever our linear data stream goes on, you see this is a very simple example that at a certain position our LLM gives us a sign, a message, whatever. Now we get an idea where we are today. But you might say, hey, wait a minute, Microsoft already published here a long net. And I have here a video where Microsoft says, hey, yeah, we have this new method for a token length of 1 billion tokens. And as you found out here in my video, where I had a deep dive into the theoretical research paper, that Microsoft could only validate this particular method on 32K token length, and everything else was mentioned as theoretically it could go to 1 billion. So maybe not the most optimal model. So let's stay here with this publication. MIT, Meta, and Carnegie Mellon University deserves here our undivided attention. In every paper, you have a main idea, that everything is on the shoulder of one main idea in this paper. And here we have the main idea. And I give you here the figure 2 of the original publication, and I give you here the exact quote here from the authors of this. And if they look here at the average attention logits of a Llama 2 model, they say that they find something. And they say that if they plot here the attention maps of the first two layers, this is okay. So we have only local attention patterns in the self-attention mechanism of the transformer architecture. But they say, you know what? If we go to higher layers, layer 2, layer 9, layer 16, 23, we find something that here, look here at the start token. Look how here given this color here of our attention. This is here an attention attractor. We have here a maximum attention. So they say now the model heavily attends to the initial token of a sequence across all layers and heads. And they say now, hey, we find an interesting phenomenon of autoregressive LLM. And a large amount of attention score is allocated to the initial start token. And they term this token now attention sinks. Okay, and they say despite the lack of semantic significance of the first token, they collect significant attention scores. So it's not a sink, but it's an attractor, but never mind. So here MIT and Meta proclaim, hey, they find an interesting phenomenon and they have something new, and this something new is the basis of their new model of this research paper. There's only a little problem with this. Because if you are working with AI system, with transformer system, with BERT system that run on attention, self-attention, you know this already. And I show you here the official documentation of sentence transformer. And if you go there and you look to the class sentence transformer model pooling, you have here using pooling, it generates from a variable sized sentence a fixed size sentence embedding. So this pooling layer is important, and how we can do this here in the sentence transformer, also an AI system, yes, you noticed it. And they say, hey, the layer also allows to use the start token, the very first token of a sequence, if it is returned by the underlying word embedding model. So here under the parameters here of the pooling layer of the sentence transformer, we have pooling mode CLS token. Use the very first token, our CLS token or start token, as a text representation. So here we already have this phenomenon, and we use this phenomenon for 2 years. And if you are here a new viewer, so for Ben here, you know, in BERT, the CLS token is very important because only the start token is used in BERT now for years for a sentence level classification task. And this CLS token is important because we know for years that it contains BERT's understanding of the entire sentence. So this start token, given the self-attention mechanism that calculates how much attention is to each word or each token in a sequence, the CLS token encodes here really important information. And if there was a viewer said, hey, okay, maybe I not qualify for Ben, but I think I'm Ben's younger brother. Would you also accept here an explanation for some younger brother of Ben? So welcome, of course. So if you like to find out more about the importance of CLS token, in this video, this is my SBERT 4 video that I did 2 years ago. I coded here with the CLS token here, the SBERT or the BERT transformer for sentence embedding. And I made a video that is 2 years old. So you see, this new discovery by MIT and Meta, yeah, maybe should have done some literature search beforehand. Anyway, we go back to the study by MIT and Meta, and they say, based on the above insights, what they discovered, they propose now StreamingLLM, and now it gets interesting. So they say we have an LLM pre-trained here with a finite attention window, 4K in the case of Llama 2, and this will work on text of infinite length without any fine-tuning. And you might say, this is really interesting. But I would need a streaming LLM, so I'm interested in this. And they say it exploits the fact that the attention sinks, or the attention attractors of the CLS token, of the very first start token in a sequence, has an important value, and we preserve them and maintain here this. Great. So what is the main idea of the streaming LLM? It simply keeps here the attention sync tokens, key V values. So this is our, if you want, our CLS token, our start token. And I will explain in a minute why we have 4 initial tokens. So they take the start token and the what we know as sliding windows KV to anchor here the attention computation. So what they do, they just combine 2 methods, the start token and a sliding window that we already know from all transformer architectures. If you want to learn more about here the query, the key and the value, and how it is calculated in the self-attention of a transformer network, and I have here on BERT network, this is the video for you. And I try to give you the most simple and insightful explanation how self-attention is calculated. So here we are now. This is now an LLM, an autoregressive transformer. Here a beautiful green box. And now it does not give us a signal, but it produces 1 word at a time. And following here the streaming LLM idea, we have a linear sequence of written tokens. So now we do not have here a coded sequence, but we have tokens that come in our linear data stream. And this is now what we observe as our simple model representation. Now you might ask, okay, so what is the length here of our string if we have infinite length? And now reading the paper, it is interesting to see that it is infinite length under certain conditions. Now, what they take a question and an answer. And now this is important because now we see that they concatenate question-answer pairs, question-answer pairs, question-answer pairs, and these pairs build up here this infinite data input, this streaming data input to their LLM. And I quote here the original authors, they say, we first concatenate all question-answer pairs here from a dataset available on Hugging Face, and then we feed the continuous stream to a Llama 2 model, this is our green box here, and assess the model completion at each answer position using an exact match criterion. So this means they look in this infinite data stream on the sequence of question-answer pairs, and they look in particular to each answer position. So whenever a question comes into our LLM, the system gives immediately an answer. So what I thought when I read here the article the first time, that we have an infinite stream, we have a chunked up stream, and we have question-answer pairs, question-answer pairs, question-answer pairs, where after each question, and it could be a very short question, I will show you the data, the system now generates an answer. And then the system gets another question, and the system generates an answer. So this concatenation, as the authors of the MIT and Meta study write, this structure becomes now infinite. And you might say, yes, okay. But this is not an infinite structure, but this would be semantic. The data set. This is on Hugging Face. I just go there, ARC challenge. What is the data structure? You have a question, whatever it is. You have choices A, B, C, D, and you have the answer key that tells you what is the right answer. So what you have simply is a question and a correct answer and some wrong answers. And from this, you can build up your streaming data, your input stream. So we use this available data. Okay. As I told you, the streaming LLM keeps the attention sync tokens, the CLS tokens, the start tokens, and I explain in a second why we have 4 tokens here in the case of Llama, together with the sliding windows key value pairs to anchor the attention computation. And they give you now an example how good their model is compared to the others. So at first here at A, we have the dense attention. This is where we really have everything to everything. This is the complete mathematical system that really calculates here our attention mechanism in a transformer. Because it is really precise, it has, if you want a poor efficiency, it takes a long time, t square. So the order here is t square. And on long text, I told you, it depends here on the pre-training, or you have to switch over to some LoRa implementation, like the long LoRa implementation. A possible solution was found with a window attention. So you do not take here the complete structure of your sequence, but you define only a limited window. And only in this window you calculate here the attention mechanism. Then you have the sliding window with a recomputation to make sure that you are on the safe track. And then they combine now here their insights into their streaming LLM. So what they do, they have here the sliding window. And as you can see here in yellow, here the very first token of a sequence. Our CLS token in BERT or SBERT or whatever you go. So this combination of window and this gives them exactly what they call now streaming LLM. So you see, it is not complicated at all. What they claimed that they found was known for years. They just give here, Meta gives here in the marketing a new name to this phenomenon. And we have a new LLM, which is rate. So figure 4 in the publication gives you a good insight what happens in addition. So let's say we have here a sequence. We are an autoregressive LLM. We have, starting on the sequence, in yellow, we have our CLS token, our start token, our initial token, whatever you want to call it. Our attention sink, like Meta calls it. So this is here, I explain why it's 4 in a second. So this is our start token. Then we have now the token of the sequence. And here figure 4 gives us from the article an example. We want to generate token 7. You know, autoregressive only looks to the left and generates one token at a time. So we look here at the token 4, 5, and 6, and we generate the token 7. Let's assume for a moment that a token is a word in our tokenizer. And here, this 3 token is today is a, and 7 should be beautiful, and 8 should be day. Today is a beautiful day. A sequence in a sentence. Now, what they do to reduce here the computation as they go along, you see here that after the start token, the CLS token, the attention sink, or whatever you want to call this yellow start token, they have here with this shifting window a rolling key value cache. They only focus now here on 2 elements, the start tokens and the window, the rolling window tokens. And all the tokens in the middle, yeah, they are gone. Because we know that the information, the complete self-attention mechanism that is calculated in this sequence, we have the importance of the CLS token here, the very non-semantic carrying start token. So this is now the insight that they use here. And in SBERT, we only used here the start token. And now, since we are working now in an autoregressive mode, we just take here a very little sliced window that we are rolling over our sequences, and only those rolling key value cache sequence is important for us. As I told you, I'm going to tell you why 4. And the authors also address this problem with their Llama 2 model. They say, why 4 initial token as here our CLS token as the attention sinks in our new streaming LLM? And they give an explanation. We believe this pattern of 4 start tokens emerges because these models, the Llama 2 model here, didn't include a consistent, clear identified start token across all input samples during the pre-training. But during the pre-training of Llama 2, something happened. And also here, the prefix of each paragraph was here a special token. It's applied before the text chunking. So the text chunking mechanism in the pre-training here resulted in a mostly random token occupying the position 0 in our sequence. And they say, okay, and this is the reason why if we have 4 initial start tokens, given that our pre-training was not consistent, with those 4, we cover the main set of possible start tokens. Interesting to see that here you have an effect of a non-optimal pre-training of Llama through breaking through, and now we have 4 initial start tokens as CLS tokens or attention sinks. So now you know where we have 4 tokens. Short summary. So to enable now the LLM streaming complexity in this model, we are now having here a combination of the sliding window tokens and the start tokens in the attention computation. So make it absolutely clear. In our cache, as I showed you the code for the Kiwi cache, in this new model, the StreamingLLM, we compute it here, and we compute 2 parts. We have our CLS token, we have our start token, or our, in case of Llama, 4 initial tokens, and the most recent tokens, the rolling cache that contains the most recent token, because autoregressive, we have to come up with the next word. I want to give you here a visual simplification that you get a feeling, and here we have it now, at different time slices here. We have an attention window, we have in yellow the CLS token, the start token, the attention sinks, the main attractor here. And if you go along now, and if you have these question-answer pairs, question-answer pairs, question-answer pairs, and then we have here the actual computation here. So here in Llama 2, we have 4 initial tokens. Then we have here a rolling cache, if you want, where we only have the latest token in the sequence, and this is here in blue. So token 6, 7, and 8, and 9 is generated here, looking here at the initial tokens and only at the latest token, and all the tokens in the middle are, not taken care of in our calculation. So you see how we achieve here, if you want, better looking back in the history of our conversation, question, answer, question, answer, question, answer, because we simply get rid here of all the middle tokens, because we know now that here our starting CLS token includes here the information of the sequence, exactly like in BERT and in SBERT, already shown and done for years. This is here a very simplified version. So you see, if this model now says, hey, our LLM streaming is better in looking back here at a long conversation and an ongoing conversation, it is because they take care here about the encoded information of our start CLS token. And they include this now in generating the next answer. Please watch out, StreamingLLM here, focusing on the position within the cache rather than those in the original text, because those tokens from the original text will not be taken into account of. So we're looking here at the KV cache position. And you can combine it with rope, and you can combine it with alibi. Never mind, this is just a method relying here on the encoding of our starting token of our CLS token. If you want it a little bit more precise, so we have here a short theoretical overview of the cache in our streaming context. You can read it yourself if you want to have a better feeling. It's about the stored key value pairs of previously seen token. So whenever a new token arrives, its very vector is compared not just to its own key value, but also with the cached key value pairs from previous tokens within a specified window size. And the previous tokens are our previous question-answer pairs, question-answer pairs, question-answer pairs from the past. So looking back a little bit here in the time history of our infinite text streams, they have now a better understanding of previous question-answer pairs. And if you assume that you have a conversation and the conversation stays on topic, so knowing a little bit more in the history here, going back here in the time, the history before the current conversation period, you know what already has been said, already what has been referred to. Let us have a look together at the code implementation. As you can see, we are in a GitHub directory. We have some examples. We have a setup. Okay, yeah, version 0.01. This is great. And then what else? Data examples, figures, StreamingLLM. So here we go, StreamingLLM. So enable streaming. Here we have the key value cache. Let's have a look at the utilities. What utilities do we have? Yeah, okay. So we have here our tokenizer. We go with here the Hugging Face, auto tokenizer from pre-trained model on Hugging Face, the model auto model for causal language model from pre-trained on Hugging Face, and here the beautiful download the URL. Okay, then let's go to the key value cache. We define slices. Okay, so here we have our class start, the recent key value cache, our rolling cache. As you see, start size, recent size, the dimension here of k and of v. We have here, okay, and we call it, yes. We have here the evict for space, and then we have here evict the range, beautiful. And you see, this is it. This is all there is to our rolling key value cache. Now, the most important Python file is, of course, enable streaming here, our StreamingLLM. So what we do, we import here our start recent KV cache. We just had a look at this. Then we enable the StreamingLLM, our model, the start size and the recent size. And here they went with multiple LLMs, with the Llama, with the MPT, with the GPT Neox, and with a Falcon model. We focus here today on the Llama implementation. Implementing Llama, we see here. What if this is the whole program? Okay, so let's go here with Llama, and we look here at the StreamingLLM, position shift and modify Llama model. So, okay, StreamingLLM, here we are, position shift. Let's have a look here. Okay, here we have our Python file to modify Falcon, GPT thing. Okay, and we go with Llama. So here we are now in the main code sequence, as you can see. PyTorch, beautiful. Transformer, yes. Llama, okay. Llama attention, beautiful. Apply here rope. You know this. Apply Llama position shift attention forward. Okay, here we have our key value slicing in detail. And if you want to have a deep dive, this is the code for you. And as you see, this was it. So from the complexity, it is not really that complex, but of course, the main idea and the theory behind the model, the implementation of this model, is what makes this model interesting. For Ben, again, this multi-round question answering scenario. And the author of the study from MIT and Meta AI here for StreamingLLM, they focus here absolutely on the multi-round question answering scenario. And they say, here, and only here, our StreamingLLM performs comparable to one-shot sample by sample baselines in a multi-round question answering scenario. Great. So for this scenario, and this scenario only, the authors say, this is it. So get an idea. So the user says, hey, what is the capital of France? Model comes back, capital Francis Paris. And then the next question, this is the first question answer pair, and the next question answer pair is what river runs through it? And now to find out what is it, we just look back here at the, if you want, older question answer pair that's in the cache. We understand that our conversation in this question answer pair is about the city of Paris. So we take this information, say what river runs through it. Now we know it is Paris. And the AI model can say the river Seine runs through the city of Paris. So this is here a very simple explanation what's going on. Now, of course, in a study, you need performance data. Please note that in this performance data, I had to smile, yeah, because the window attention and the streaming LLM, they use a cache size of the model of the LLM of 1K. Now, I have, I think, never worked with an LLM with a cache size of only 1K, but I understand if you want to promote your own model, you find a system configuration that shows how good your model is. And so let's follow here the official table 5 here of this research paper. And here you have the model. You have the Llama 2.7b, the Llama 2.13b, and the Llama 2.70b. And as you can see, if you go here with a simple one shot, you have here this performance measures. Great. And now comes here the surprise. As I showed you with the dense, with the complete attention mechanism, with 1K cache size, you run out of memory. Oh, what a coincidence. Then if you have here the window where you use here on a 1K, this specific window configuration, your performance is not good at all. I wonder why. But if you, let's do this. So you remember dense here, complete to complete. Window, we have here the sliding window. You could do a recomputation, but this would need time. And time is what we do not have in our computation. So the streaming LLM combines, as I told you here, the CLI start token and the window structure. So window is still not good, but of course, if you take now the streaming LLM, yippee, you have now a performance that is comparable to a normal classical one-shot performance. Okay, and I thought, great, but can I use this now for my personal use case? Because I have data streams that come in continuously. So, and they claim that the streaming LLM is capable of a 4 million token length. So they also reduce infinity to 4 million token length in the depth of the research report. Okay, so I say good. I take this 4 million token length. I assume that 4 million token is about 1 million words. So let's make it very easy. Now my sentences, science, theoretical physics, AI, sentence has about 12 words, plus minus, never mind. So this means my 4 million tokens is about a sequence in my domain of more than 83,000 sentences. Now, as I told you, StreamingLLM uses for a Llama 2 model a context window of 4K. And I have now sentences of I have more than 83K sentences. So can I use this for my particular LLM, for example, summarization example? Yeah, and as you guessed it, the answer is with a streaming or context window of 4K as the use here, you cannot feed in data that exceeds here the window size, because otherwise it would be neglected. So yeah, let's put this here in a word. So storing all previous key value state demands significant more memory, and the models might struggle to generate text beyond their pre-training sequence length 4K for a Llama 2 model. So the streaming LLM addresses this by retaining only the most recent tokens and the attention sinks disregarding the intermediate tokens. So if I have here 4 million tokens, the last 4K token in a summarization test will be regarded, and I lose 3.996 million tokens. Okay, so, and they also say, and this is here a quote, while you can input a lengthy text, let's say 4 million token, this model will only recognize the latest token. Since it's now not a sequence of question and answer, question and immediate answer, question of immediate answer, but we have now a continuous data input stream. Like example, we take a book and we take the whole book as an input. This streaming LLM, and this is what they also say, might only summarize the concluding paragraph. So the last 4K tokens, which might not be very insightful if you want to understand the complete publication or the complete book, the content of the complete book. So as emphasized earlier, we neither expand the LLM context window nor enhance their long-term memory. So for this task that I'm interested in, so not, I don't know, what I say here, WhatsApp chat or whatever, where you have a very short information and you want a system to answer, and you have these multi-conversation rounds, but I want to feed in information. Only the last paragraphs, only the last 4K tokens are analyzed by StreamingLLM. So here we have it now, the official streaming LLM by MIT, by Meta AI and Carnegie Mellon that says, hey, we deploy LLM for infinite length inputs without sacrificing efficiency and performance. Now, let's say this is now in the research publication, the part where I would say this is the marketing part of this research publication. And we just find out the insights that you are specific. I can't use here an infinite token length input of this new streaming LLM for a simple task for LLM summarization, because everything that exceeds the pre-trained Llama 2 context window size of 4K token is neglected. So this here is the marketing and the official heading of the research paper by MIT and Meta. And this is what we end up with after having analyzed now the content, having looked here in detail at this specific research paper. So we find this streaming LLM is only valid here for a very specific use case of a multi-round conversation, which is of particular use only for a very narrow part of users. So there we have it. Now we understand exactly here the latest research, end of September 2023. What streaming LLMs here is here the research insight and what you can expect here coming up, of course, for the cooperation Meta and Meta AI for your other apps that are from this company. Thank you, and it would be great to see you in my next videos.